Let's talk about the albedo effect, a crucial architectural concept. I developed an environmental metric that explores this phenomenon. Albedo measures how much sunlight a surface reflects, with light surfaces like snow reflecting more light and darker ones absorbing heat. This affects urban temperatures, energy use, and sustainability. The albedo effect ties directly to climate change. Melting polar ice exposes darker water, absorbing heat and accelerating warming. Similarly, urban areas with dark materials create heat islands, raising temperatures and energy demands. Reflective or lighter materials in construction can help counter these effects. By analyzing roof and wall materials, we found that typical Ottawa homes with brick walls and asphalt shingles had albedo values between 0.20 and 0.30, too low for meaningful energy savings or cooling. Using reflective roofing, radiant barriers, or lighter materials can reduce energy costs, improve comfort, and mitigate heat islands. High albedo designs in sunny areas like Ottawa and globally can combat climate change and promote sustainable, eco-friendly homes.
The next metric assesses residential lot design in the face of temporary flooding caused by rainfall. I calculated the intake a lot would receive on an average day of rain and compared it to the record 44 millimeters of rain that caused flooding in Ottawa this year. I estimated the daily water absorption rate of Ottawa soil from a soil sample on Site A. From that information, I calculated how much permeable area one would need and compared it to the existing space on the lot. The single detached homes on Site A and B would have no trouble absorbing the rainwater. Site C, however, is a townhouse and would experience flooding on an extreme weather day. The results demonstrate how climate change has a stronger impact on those who rely on affordable housing. Trees or lawn versus garden coverage impacts as well how much water can be absorbed and retained on a lot, but the biggest impact would be changing driveways or walkways to permeable paving. This metric can be expanded from individual lots to cities. It would be useful in organizing citywide action for more permeable design to ensure the health of watersheds for future generations and reduce stress on city sewage systems.
So the metric I developed measures the amount of carbon dioxide sequestered by trees and grass areas of any given site. With some research values, I was able to attribute the annual carbon sequestration rates of several common trees and plants, and using this we're able to sum these values to find the total carbon dioxide sequestered per year through these means. To make this more accessible, I created a simple Python program that calculates this for you. Here's a quick example. Let's say if we had a residential lot with 50 square meters of your standard lawn grass and 2 oak trees, the program estimates a total of 40.18 kilograms of carbon dioxide absorbed throughout the year. Although this metric isn't perfectly refined, I think it shows great potential. It can push the average person to be more sustainable in ways they can achieve themselves, like allocating more space for greenery on their own property. It provides tangible and realistic sustainability goals, encouraging a more eco-friendly future.